And your talk is on counting spheres and disks in the cubic surface tropically. We will be recording this, but only sharing this with other participants. I'll let you go ahead.
Okay, thank you. So thanks very much for the invitation, and hope to see you all in beautiful Spain sometime again before too long. So this is joint work with Sushmita Venugopalan, who's in Chennai at the IMSC. And it's a talk about a particular example of the cubic surface. This is a particular sculpture of a particular cubic surface called the Klepsch cubic surface, whose equation is written down at the bottom of the screen. And yeah, feel free to interrupt with questions. Should I open the chat, or is someone going to watch the chat for me? Yeah, just let me know if there's something that appears.
I'll watch the chat for you.
Okay, yeah, thank you. Okay, so by a cubic surface, we mean a non-singular variety cut out of complex projective space P3 by a homogeneous cubic equation. Particular example would be the Fermat cubic, which just means you take the cube of each variable and you set that equal to 0. And Cayley showed that any cubic surface contains finitely many lines, and Solomon showed that this number of lines is 27. This was in a series of letters between the two of them. And so this result's now called the Cayley-Salmon theorem, and it's considered one of the highlights of 19th century mathematics. There are quite a few books written about this result and its variations. Saying it's one of the highlights of the 19th century mathematics means that I initially thought, well, I'll read the literature about this and familiarize myself with what's been written, and I realized it's impossible because there's so much written about this particular result. But there's a wonderful quote from Manuel about this result and its variations in his book. He wrote, "Their elegant symmetry both enthralls and at the same time irritates. What use is it to know, for instance, the number of such lines?" So, it's like 27, but why should we care? Well, the classes of lines generate the Picard group, and the action of the Galois group preserves the symmetry, and it contains an extremely large amount of information about the arithmetic and geometry of the cubic surface. And there's a more modern viewpoint on what it means, this extremely large thing means. So mirror symmetry posits that to any symplectic manifold, there's supposed to be a complex mirror manifold, and this should be equipped with some sort of potential. And this potential counts not holomorphic spheres, but holomorphic disks. And then you're supposed to get sort of an equivalence of theories, and it's not really exactly understood what that's supposed to mean. But in particular, Lagrangians in your original symplectic manifold, they're supposed to be equivalent to some sort of jazzed up version of vector bundles on the mirror side. And the quantum cohomology, which in particular tells you the cohomology, is supposed to be the Jacobian of W. So this is the ring of functions on the critical locus of this function W. So mirror symmetry is supposed to be, roughly speaking, an equivalence of categories. In other words, if you construct the mirror, you're supposed to be able to apply mirror symmetry twice and get back to your original category. For example, a symplectic category. That's not quite true. There are these things that are called double mirrors, where if you do mirror symmetry twice, you might not get the same variety. But these are relatively rare. So in the modern perspective, Manuel's extremely large amount of information has actually been upgraded. These kind of counts contain essentially all of the information about the symplectic manifold that you might be interested in. Yeah, this count of 27 lines, it's one of the first interesting counts of these holomorphic spheres, which are called Gromov-Witten invariants. So what are the Gromov-Witten? Okay, well, first let me do just why are there 27 lines? So this, Mumford has a really quick argument in his book on complex projective varieties. So the argument goes like this. So you first reduce everything to the case of the Fermat cubic, which is there anyone that came in late and didn't catch the definition of the Fermat cubic? Just ask if you. So this was the thing where you take the sum of the cubes of the variables and set it equal to 0. And so then, after permutation, every line in P3 can be written by, you're trying to cut down the number of dimensions by 2, so there should be 2 linear equations. And you can assume that after permutation, it's given by Z0 for some constants A and B, AZ2 plus BZ3, and then the second variable should be expressed in terms of the last two as CZ2 plus DZ3, and there are going to be some constants A, B, and C here. And so then when is it in the Fermat cubic? Well, you just have to plug in this into the sum of the cubes equals 0, and you get the equations A cubed plus C cubed plus 1 equals 0, B cubed plus D cubed plus 1 equals 0. And then there are two other equations here, which involve cross terms. And what you see is that if these are all non-zero, then this is just impossible. You can sort of play these equations against each other a little bit. Like you can divide the third and the fourth equation by each other and so on. Okay, you get some relations among the A and C, B and D, and so on. Okay, so one of the coordinates has to be 0. Let's suppose for existence A is 0. Well, if A is 0, then you go back and you look at this equation here. If A is 0, these terms are gonna go away. And but the fact that A is 0 means that C here can't be 0, and but then that means that D has to be 0 from this last equation. So, and then you solve for B and C, and you get that B and C have to be minus one of the roots of unity. So omega here is a cube root of unity, and B and C have to be in this set -1 minus omega squared. So that there are 9 possibilities here, and because you're deciding which of the coordinates, 2 of the coordinates to be 0 and the others are non-zero. 4 choose 2 divided by 2 is 3, so that gives you the 27 lines, and you can write them down explicitly as these 3 equations here, where I and J are some powers of the omega root of unity. Okay, any questions about that? It's Mumford's chapter about this in his textbook is really well written if you have never seen it. Okay, so we want to talk about a way of doing this using sort of toric geometry and moment polytopes, and the motivation is to try and get the disk count in the same way that we get the sphere count. So there's a result of Clebsch which says that any cubic surface can be obtained by blowing up 6 points in the projective plane. So what that means in terms of the toric geometry is that I'm starting with some polytope. Let's say I start with a polytope for P2, and then I start cutting off the corners. Okay, so actually the original edges here in my P2 are say these 3, something like this I could do, and then I'm going to add new edges by just repeatedly blowing up. So I could say cut off this one and then cut here. I didn't do that right, sorry. Cut off here, and then cut off here again. That'll introduce some new faces. and do the same thing up here. So cut up here, and do here. So that introduces 16 faces. And then I get the polytope that's shown on the right. And well, if I move the blow up points, instead of taking the torus invariant points to blow up, if I take generic points, then I'll get the cubic surface. So the cubic surface degenerates to this toric surface as I move the blow up points to special position. And so the last blow-ups in the sequence are actually the long edges. It's usually you think of the blow-ups as creating short edges, but here I'm taking them to be long edges. And if I blow down the short edges, then I get some polytope like this. And this is something with orbifold singularities at the vertices here. So there'll be 3 A2 singularities at the vertices of this toric surface. And I can think of the smooth toric surface on the previous page as a resolution of those A2 singularities. Any questions so far? Okay, so so a Gromov-Witten invariant means you count the number of stable maps of some degree, and by this I mean homology class. And as in general, as the degree gets larger, in this particular case, the dimension of the space of maps gets larger. So you have to cut this down by a constraint by requiring that they pass through d-1 points. If I'm just looking at lines, then d is 1. And so there's no constraint. And this is Cayley's result that there are finitely many. So this Cayley-Solomon problem is basically saying you want to compute the first non-trivial Gromov-Witten invariant of the cubic surface. And one of the key properties of the Gromov-Witten invariants is they're invariant under deformation. So you can in fact just hope to compute these using the toric picture. And so Gromov compactness means that any of these 27 lines in the cubic surface is going to degenerate to a collection of holomorphic spheres in the toric surface. So the picture is, if I have my line, which is a holomorphic sphere in X, then it might degenerate to something like this. Okay. But one observation is that if you have a sphere in this collection which is not invariant, so something like this, well, this is going to meet the boundary in at least 2 points. So the churn number here would be at least 2. So that's rules out these possibilities of degenerating to interior curves, and you're just degenerating to boundary curves. And so these 27 lines have to be deformations of some combinations of the spheres corresponding to the long and short edges. And the total churn number has to be preserved in this deformation. So the question is which combinations of the edges correspond to these 27 lines? Okay. Well, so first, let's just look at churn number. So churn number means that I look at the pairing of the homology class of the curve with the first churn class of the manifold. And in toric geometry, there's a simple way of determining what the churn numbers are. You look at the sum of weights at each fixed point, and then you take the difference between the weights on one vertex and the other vertex, and then you just divide by the direction of the edge. So the point is that something like this edge corresponds to a sphere of churn number 1, because if I start from this edge here and I go to this edge here, then these two edge vectors are related by exactly adding on the direction of the edge that they're separated by. But this edge here, this would be C1 equals 2, actually. That's a harder one. I guess I was going to do, let me just explain. Maybe this one. This one is, no, I didn't do that right. C1 equals 0, sorry. Oh, this was the normal bundle. Okay, sorry. What did I do wrong? I wouldn't just say that this one was C1 equals 0. Right, so the fact that you go from the outgoing edges are related by some multiple of the edge itself that connects them, that gives you the normal weight. And then you have to add on the tangent weight, which is 2. So that shifts it down from 2 to 0. So I have the churn numbers are as labeled here on the picture. And so I'm looking for combinations of these edges which sum up to churn number 1. Okay, so there are ways of doing this in algebraic geometry. So Gotcha and Pandarapanda computed the Gromov-Witten invariance of blowups of the plane using the Cremona transformation. And the idea here is that you can sort of blow down some of the lines and blow up some other points, and then you can compute all of them that way. And Brian Lung showed using their results that if you have a resolution of an AN singularity, then the strings of churn number 0 spheres contribute exactly if they are non-self-crossing. Okay, so the Brian Lung result can be applied to this case, and it does give the right answer of 27. So let me just maybe start drawing spheres, and you'll see how to do it. Okay, so one of them, we wanted churn number 1. Okay, so one of them is like this. That's a churn number 1 sphere. But also the adjacent spheres here are churn number 0. So I can do this one, or I can do this one, or I can do the same time, or I can keep going. So I could do, say, this one, this one, this one, this one, this one, this one. Well, okay, so that's the first however many 6. Okay, so you just look at all sort of strings like this, paths of non-self-crossing paths of edges along the boundary, which contain exactly one of the churn number 1 spheres and however many numbers of adjacent churn number 0 spheres, and that gives you 27. Any questions about what the 27 lines look like? So from the point of view of moment polytopes, the whole computation is just a little unsatisfying because you have to get rid of the toric picture in order to compute the number of spheres with churn number 1. And we usually the toric geometry gives you some advantage in computation. And so we want to give a computation which uses the toric structure rather than forgetting it. So, and another motivation for this is the discount. Okay, so Sheridan in 2019 conjectured that the number of disks bounding a Lagrangian torus with relative churn number 1 should be 21 instead of 27. So if you think in terms of how a physicist would describe that, they would say there's a closed string count, which is due to Cayley-Solomon, which gives 27, and the corresponding open string version is 21. So what do those disks look like? So So some of these disks are easy to describe. Okay, so, for example, if I have my original P3, remember my X is the blow up of P2 at 6 points. And so, in my original P2, I can just take maps like this, Z goes to Z11, and just restrict to Z having absolute value less than or equal to 1. And so in the moment, the image under the moment map of these disks looks something like this. Or maybe there's one here, there's one here, and there's one here. And I've just choose they don't intersect the torus fixed points. So these disks survive into the blow up. And there are going to be other Blaschke products which go to these other facets. Sort of, you just have to look at the similar coordinate description in the description of the toric variety. Okay, so this gives me 9 disks so far. And so I'm missing, not 18, but what's 21 minus 9? I'm missing 12. Okay, missing 12 disks. And so one thing you can do is you can sort of finesse the sphere account. So there was a paper of Chen, Lao, Cho, and Sang, which says, well, they can reduce the disk count to the sphere count. But then I'd like to do this just using the toric geometry, not by switching to some algebraic geometry approach and then doing a Cremona transformation. I really want to see the disks in this picture. Okay. So so the context in which I'm going to describe this is about multiple cutting. So this was investigated by Eugene Lehrman and Eckhart Meinrinken and other people in the 1990s. This language of tropical maps and manifolds was, as far as I know, introduced by Gross. And I sort of like this terminology, so I'm going to adopt it. So what do we mean by a tropical Hamiltonian action? Well, we mean that you have a triple X, phi, and P. And so you have a symplectic manifold, you have a Lie algebra T, and you have a decomposition of the dual of the Lie algebra into polytopes. And then you have a map, which is just C0, which is compatible with the decomposition in the following sense. Well, if I look at the perpendicular to the tangent space of P at any point, and I take the corresponding torus, then I want to get a moment map for the action of TP on some neighborhood UP of the inverse image of P. So for example, if I started off with, say, projective space, let's see, I wanted to just change color. Okay, so I could start off, say, with projective space, and my polyhedral decomposition might be something like it might decompose the triangle into these 3 pieces. So this might be P1, P2, and P3. And then I would get from this 3 cut spaces, I get this is one cut space, this is another one, and then the third one would be this square. Okay, so this is the process of multiple cutting that the definition is you just take the inverse image of each polytope, and then on the boundary there are these torus actions, and you collapse the torus actions to get these things called the cut spaces. Okay, so I don't know what happened to the picture here. There was a picture, now it's disappeared. So in my example, I had the cubic surface. There were 3 long edges and then 3 short edges. And so then I choose some decomposition, which is going to separate each of the short edges into 2 pieces. And I'm probably going to get the slopes wrong. But let me maybe move ahead to where I'm sure I showed the picture so I can remind myself what it looks like. Okay, so it's up, right, and down left are the directions. Okay, so the directions are up, right, and down and left. And then I just sort of connect these up to give me a polyhedral decomposition. And so now the question is, like, how do I compute these sphere counts and discounts, using counts in the smaller pieces x sub p. So symplectic cutting and symplectic geometry, it gives you a possibility of doing something like Meyer-Vietoris, the way that you would compute the cohomology by looking at what happens locally and then seeing how everything is going to glue up. Okay, and so in order to make this work, I need to assume that there's something called a gluing datum, which means that it's a collection of polytopes sort of in the perpendicular direction to the p's. I mean, if this is my p, then my p perp is something like this. P dual is something like this. And so if I take p times p dual, that gives me some sort of thickening of my original polytope. And there's some sort of compatibility condition here that I'm not going to talk about. But if you want to cut up, say, a picture like this would sort of represent a Hertzebruch surface. Then I want to assume that there's a way of thickening it, each of these pieces, so that I get a picture like this. And this parameter here is, I'm free to choose how big this is. This t is like the neck length here in the language of Hofer. And then we want to take t to infinity. Okay, so this is the limit in which we can expect to get a good description of the holomorphic spheres in terms of the, or disks in terms of the local pieces in X sub p. So yeah, so this is just what I said before. The p times p dual should be a tubular neighborhood of p. And so then there's something called the dual complex for the gluing datum. So this means you take all of the p duals and you identify them along the boundary. So if I would take something like my original example, I was taking, let's say the polytope was P2, and I cut like I said, so I cut like this. Okay, so then this was P1, P2, P3. P1 dual is just going to be a point. Because there's no, P1 is something of maximal dimension, so there's nothing there. So P1 dual is here, P2 dual is down here, P3 dual is down here. And then I connect them up by the duals of the other one. So here P12 would be here, but the P12 dual would then be a segment connecting P1 dual and P2 dual. So I get this picture again. And it's just an accident that I get the same triangle. So that's what we say when we mean that a triangle is self-dual in this sense. Okay, and then this would be my dual complex B dual. So okay, so the limits of holomorphic curves under this map, limiting map, are going to be curves associated to some graph, which is called a tropical graph. And so what does a tropical structure on a graph consist of? Well, first of all, for each vertex, you want a polytope, one of these polytopes in the polyhedral decomposition that I'm using for the cutting. And then you want to assign a slope to each edge, which is called T of V. That's like the T stands for tropical weight here. And then there should be some conditions on these data. The tropical weight. Oh yeah, so then there should be a T of V for each vertex. And the difference of the T of V's between any two vertices connected by an edge E should be some multiple of E. So T of V plus minus T of V minus should be in the span of T of V. Okay, and then a tree graph together with a tropical structure is called the tropical graph. Any questions about this? A lot of this is from the work of Brett Parker. Okay, and so then a broken map, which we write as C goes to XP for short, means that you have a tropical graph, some domain thing. So the domain thing looks something like this. It might have some spheres attached. And then for each of the vertices in the graph, you get a map from some part of this domain C into the cut space, actually corresponding to the thickening. Okay, so in this thickened picture, the original things are sort of thickened up a little bit. And so there's going to be a cut space associated to each of these thickened edges. And I want, XP of V bar means the thickened thing. And I have a curve in there. So the image of the curve looks like some sphere in this thickened piece, sort of like this. And you want all of these to sort of match up. So I could maybe go over here for a while. I could go through this piece, and then I could stop here. That would be a typical example of a broken map. And then there's some continuity and edge matching. So what that means is that, not only at the places where these spheres intersect, they should not only sort of match up horizontally, but also the direction that each is coming into the or leaving the node should be the same. Okay. So these are called matching conditions, and yeah, another way of writing it is to say that if I can choose local coordinates Z plus and Z minus near the nodes, so that if I use the torus action to write Z minus to the TE, you have to think about why that makes sense, and then look at the U minus, Z minus, and U plus, C plus, then these are going to have the same limit. Okay, so then there's several results about these things called broken maps. So So there's a generalization of the bourgeoisie-Shapiro-Wazowski theorem, which says that if I have something with bounded area, then there's a subsequence, the Gromov converges to some limit, which is associated to some graph. And then in the case of isolated points, and if you're doing a count where the disks or spheres are finite in number, then this actually gives you a bijection between disks in your original space and the broken disks in the degeneration. You see, here's a sample picture of what this might look like. In your original manifold, you might have a curve that looks like this green guy. And then in the limit, these sort of spheres, 5 spheres that are sort of drawn as slightly more rounded, might sort of map into different cut spaces. So that associated to each of these dots is some sphere. And then we just record, this neck, these neck regions become just edges of this tropical graph, gamma.
Sorry, is this again using the method of 27 lines or 27 cuts?
This is the general story. And then the cubic surface is going to be, I'll say in just a second how this applies to the cubic surface. So this would even apply, for example, you could do this with P1. Okay, so P1, for example, just the sphere. I could apply symplectic cutting to this, and I could cut it into 2 pieces, right? So here the polyhedral decomposition would just be the positive axis and the negative axis. And so the dual complex would just be an interval. So that would be P dual. So what happens to just P1 itself when you do this, cutting? Well, P1 itself separates into these 2 pieces over here, right? So I assign to each of these pieces a vertex. So this is one vertex, and this is another vertex, and I assign to this node an edge, and that's my graph gamma. Does that make it more clear? So this is like a general phenomenon of what happens when you do cutting, and you want to see what happens to a curve under the cutting procedure.
I see.
And we want to apply that to the cubic surface to reproduce the 27 curve count. Okay, so here's the multiple cutting for the cubic surface. Is it too small? So this is the sort of the way that I'm cutting. I have sort of cutting by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm using 12 edges to cut. This was my original moment polytope. And so the little, here you can sort of see how many pieces I cut my original polytope into. And so now what I want to do is I want to say I want to have curves in each piece which sort of match up properly at the edges. So those I'm going to draw in green. Let me change style to green. I can enlarge this. Okay, so yeah, so here's one in particular. Like I could have a piece that's just inside one cut space and doesn't go into any other cut spaces. But I could also have, go from one cut space to the other by going over one of these blue edges. So the first example, there's just one vertex. So the tropical graph doesn't have any edges. And in the second example, there are 2 vertices and 1 edge. And well, then I can do the same thing on the other side. Or I can sort of have tropical graphs with 3 edges. So I could go here and then I could go here, and then I could go one more, and that would produce this example. Okay, and then this example is just this example slightly just rotated. Okay, so then you just keep going, and you can just count the number of graphs like this. So this is 9 graphs. This gives me 9 of the lines on the cubic surface, but I can do this starting with any of the long edges and get a similar description of tropical graphs, including that long edge. And so then you get 9 times 3 equals 27 this way. So Amna, is it? I mean, I haven't justified why the spheres match up this way, but this is the general idea.
The spheres are all kind of not putting it correctly, but they're tropical graphs is what you're
right. Yeah. So it reduces the computation of the 27 lines to tropical graphs. Okay. That's right. Yeah. For a particular dual complex. So these are graphs in this dual complex over here. Okay. So I started, the 3 long edges are the ones at the vertices, and I have to start there, and which one are the long edges? Maybe I just got confused here. No, yeah, this is right. Okay, so yeah, it's tropical graphs, which are subgraphs of this dual complex graph over here on the right. This is the B dual. Okay. And then this answer also works for disks. So if you start with the Lagrangian L, which is sort of just the torus, Lagrangian torus orbit in the middle, then I'm representing the disk components of the domain. I'm drawing as sort of these open vertices here to distinguish them from the vertices that correspond to spheres. So upstairs, this is the moment picture, but sort of upstairs, the picture looks like this. So that's some disk. And these disks automatically have in the broken limit, they automatically have at least 2 vertices because they're going to go all the way to the boundary. And to get to the boundary, you have to pass through one of the blue lines. Okay, so the simplest of these is this picture. This is one of the Blaschke products that I wrote down before. This would correspond to something like the Blaschke product Z11. And but then you have these more complicated tropical graphs, which are lying in this dual complex. Okay, well, yeah, now I'm a little confused. I think this is the right dual complex, and somehow there's a mistake here. Somehow some of the vertices got dropped here in this picture. That's why I was getting confused. So this picture actually, maybe when I transferred this is the correct one, and this is not the correct one. So I think there's supposed to be 4 things on every edge. Oops, I used the zoom annotate instead of the annotate for the PDF viewer. Hold on. Just stop annotating. Try again. Why is that not working? Style, blue, and then I want to draw a couple more. Oh, there we go. Okay, so there should be 4 on each edge. Okay, oh yeah, this is the correct picture for the B dual. Sorry about that. So now, yeah, so now you just get, again, it reduces to tropical graph counting. So we have the simple ones, which just correspond to Blaschke products, which just have 2 vertices, but now you have these more complicated ones, say involving 3 vertices, 4 vertices, or 5 vertices. Okay, so here I've written down 7 tropical graphs. So that gives me 7 disks. But now I have to multiply by 3 because my initial direction doesn't have to be to the right. It could be also up. So this gives me there's a Z3 symmetry here. This gives me 21 disks in total. So this was Sheridan's conjecture that for this particular example, there are 21 of them. So, under some strong assumptions, we proved that any curve count can be written as a sum over decorated tropical graphs of a product over all vertices, where the multiplicity is a count of curves in some cut spaces. And so it's sort of a generalization of the Mikulkin curve count theorem for P2. And we expect that something like this is true in general, but we certainly can't prove it. We proved it in some situation, like if you assume all of the cut spaces are toric and the Lagrangian is just in one piece, and so on. And the main application of this technique is in fact not to actually as a computational technique, as I've explained it, but once you know that you have this broken limit of the whole story, then you can actually show some general statements about Lagrangians that come from this picture. In particular, the Thor cohomology is well defined. But it'd be interesting to develop this as a computational tool more generally. We can also compute a few other examples, such as the AN resolutions this way. But if you wanted something like a formula for the number of disks in arbitrary toric manifold with constraints, I don't think that we would be able to do that. Okay, so I'll stop there. Thank you.
Thank you very much. That was absolutely, yeah, brilliant. So does anyone have any questions? I do have a question. My internet did go off for a bit, which was a shame. But you spoke about kind of the churn numbers according to the edges, and therefore figuring out from there. But then you start the second example. Maybe you spoke about this when my internet was off. But then you start from an internal point. Oh, that's the count of disks. That's where I missed. Yeah,
that's
sorry.
right. Yeah. So there's also a way of disks in toric varieties. I mean, let's just do the case of P2. So here's where we were talking about, say, spheres. And so we computed the churn numbers of the spheres just by sort of looking at how much angle there was in some sense between the outgoing edges here. Like here, to get from this edge to this edge, you would add on twice this direction. So that tells you the normal bundle is in O of -2. And then the tangent bundle to a sphere has churn number 2. So 2 plus -2 is 0. So that's how you get the churn number for the spheres. Now, if you want to start talking about disks in the interior, then there's a very simple description of disks, which are these Blaschke products. So it looks like something like it's a product of Z minus A, 1 minus A bar Z. And then you allow, you put a subscript here, I and J, and you take a product from J to be 1 to I sub L. And then you have I going from 1 to whatever the dimension of the, so this is writing a toric variety as some symplectic quotient of some big Cn. And so then you have these if I have a map to Cn that avoids the, unstable locus, then I get a map to X. So in these coordinates, every disk just looks like this. And the churn number is just the sum of the I sub L's. Is that what I called it? J. J equals 1. I need some other notation here. J equals 1 to, usually these are called D sub i's. Okay, so then the churn number is it's just the number of factors in this expression. I could take, I was talking about these Blaschke products. So these have relative churn number 1, because there's only one power of z. But if I change this to a z squared, then it would become relative churn number 2. And the relative churn number is half of the Maslov number. So it would be, these would be Maslov index 4. So then I don't, yeah, that's all I need to know about the churn numbers. What it means is that if I'm computing disks in the cubic surface of relative churn number 1, then I can only have one power of z in the Blaschke product. And so then that essentially means there would be only 3 possibilities if I was doing P2, but since I've blown up P2 6 times, that means there are 9 possibilities coming from the Blaschke product.
Oh, I see.
Yeah, and that's enough to pin down what the possibilities are.
Manuel, did you want to say something?
Something. It's okay.
Okay. Okay. So also, so I see you started, for example, here with a particular product, like the triangle, and developed it. Have you considered other shapes and such, or?
Well, this sort of, I mean, the thing we were thinking about most recently was just how to do the AN resolution. And for the AN resolution, the picture of C2 mod Zn, it's just the toric picture is you just have a sector like this, right? Where the edges are direction 0, 1. And I guess N1 would be the other edge, outgoing edge. Okay, and then you resolve it by doing a bunch of blowups. So you cut off until you get something smooth, and that's the AN resolution. And there you're supposed to get the binomial coefficients as the discounts, and so we managed to reproduce that, but we haven't gone much farther than that. There are lots of other examples here that one might try and do. We haven't gotten around to it.
Yeah, because I was just wondering about every time that the 27 lines, you always get the 27 lines and 21 disks. So you said it's always, I mean, you expect that with every type that you try, you always get that result.
You mean every cubic surface or every?
Yeah. I guess. Sorry. Yeah, I guess every cubic surface.
For other toric surfaces, the answer would be different.
Okay.
So for example, if I take the A3 resolution, then so this is something whose polytope has 3 little edges down here. Then the coefficients here, let me see if I can remember what they are. 1, sort of, oh, I guess this would be what the 1, 2, 1 would be the coefficients. So here you expect to get 4 disks. Yeah, and in general, yeah, you add up all the binomial coefficients, you get some n choose k or something, right? So in general, for the AN resolution, you're supposed to get n choose. Well, hold on. yeah, and anyway, the number of disks are supposed to be binomial coefficients in that case. So yeah, it depends on the particular example that you do.
Okay. And how did you, sorry, does anyone else have a question? Yeah. How did you get onto this? How did you, because I remember the last time that I saw you 6 years ago, it was something else. It was kind of actions on CP1.
Yeah, I guess, you know, this question of like, is Floer theory well defined?
Oh yeah, you were doing Floer theory, yeah, for sure.
Yeah. So in general, you know, the problem with Lagrangian Floer theory is you get some operator D, which you hope that D squared is 0, and then you can take the cohomology, but it's just not true in general. So the question is, in which situations do you have D squared equals 0? And if you can put yourself in some situation like this, where you can degenerate to something with simple pieces, then it's true.
Yeah, certainly like a very useful tool, definitely for evaluating complicated spaces.
Yeah.
Through the cutting. I feel like I've hogged you enough. Does anyone else have any questions? No. Okay, well, thank you so much, Chris. Really, it's been such an amazing talk.